Good morning, Brienne. I am not a scientist, but sometimes I wish I was. Science really catches my fancy. Is that even a saying? Catches my fancy? First off, I need to apologize because I might do some reading instead of just talking to you. I might be reading off my paper here because I have some numbers and stuff like that because this is a science video and I have a bad memory. As we all should know by now, NASA has a stated goal of reaching interstellar space travel by 2100, and that's really exciting, and it's good because we're destroying our Earth faster than we can save it. So sooner than later we're going to need to get off this planet and go somewhere else. Kepler 22b, I'm looking at you. And that got me thinking. Our measurements of time are based on the rotation of the Earth and the orbit around the Sun. So that's specific to Earth, so when we leave Earth we're going to need something else. And our measurements of distance, they're based on absolutely nothing at all. They're just arbitrary measurements based on the necessity to need to measure. But as the scale gets larger to interstellar travel, there's a measurement we use called light years. And this is the distance that light travels in a year. So it's not a time like the word year suggests, but it's a distance that the light travels in a year, which means that's also based on Earth as well, based on an Earth year. So I was trying to think of a measuring method that is universal, that can be used anywhere in the universe, which I guess is what universal means. You know, if Canada happens to colonize a... Sorry, I can't keep a straight face. If the US decides to colonize a couple planets out there, they'll undoubtedly want a method of measurement and time that will unify the planets. So what can we use to measure that is supposedly universal? The only things I could think of were the speed of light, obviously. The speed of light in a vacuum, rather. That's constant and it's always the same. And the size of an electron. But unfortunately we don't have a defined size for electrons as far as I know. So I decided to go with proton. And proton works well too, because it's the largest basic particle. So the size gives it a good reason to use to measure. Although I said they were a basic particle, they're not actually basic. They are made up of things called quarks, but I won't go into that now. I've talked about that before too. I'll make a video about it someday. So I went with proton. Bear in mind, I am not a math magician, nor a scientist. So my math may be wrong, and I could just be wrong about everything, but bear with me. Hopefully it gets my point across. Our method of measurement isn't going to change overnight, but likely the scientific world would take to a new measurement system earlier than the entire world would. Probably after 50 to 100 years of scientists using this measurement system, or any new measurement system, the rest of the world might finally catch on. So, what exactly would the measurements be? I'm going to start reading now. For the purpose of relating measurements so you can understand the size of them, I'm going to relate them to some normal measurements we have. The size of a proton is 1.68174 femtometers. Femtometers? I don't know. I'll go with femtometer. In a millimeter, there is 1 trillion femtometer, which means the amount of protons that it takes to make up a millimeter, almost 600 billion. So here are the measurements that I came up with, and we'll start with the ones for basic planetary needs, like inches and centimeters, meters, kilometers, that sort of thing, the measurable on Earth one. So down at the lower end of the scale, we have 1 HTP, which is a half trillion protons, which is around 1 millimeter. Then we have 1 TP, which is 1 trillion protons, which is around 2 millimeters. Then 1 THP, which is 2.5 trillion protons, which is around a centimeter. Then we have 1 TTP, which is 10 trillion protons, which is around 4 centimeters or 2 inches. Then we have 1 TFP, 25 trillion protons, which is around 10 centimeters or 6 inches. And 1 LPM, which is a large proton measure, I call it, and that's around a meter. Then 1 QSP, which is a 1/4 sextillion protons, and it's around a kilometer. Then for space travel we need larger measurements, so I did some of those too. We have 1 TFS, that's 25 sextillion protons, which is around 100,000 kilometers. 1 BGM, I call it a basic galactic measure, which would be a basic measurement for within a solar system or galaxy. That's 250 sextillion protons, which is around 1 million kilometers. And we have 1 LGM, which is a large galactic measure, and that's 250 septillion protons, which is around 1 billion kilometers. And finally, 1 UTM, which I call a universal travel measure, and that's 250 octillion protons, and that's equal to about 1 light year. It's less than a light year, but around there. And that's 1 trillion kilometers. Okay, so that works for measuring distance, but what about time? When we leave Earth, we're still gonna wanting to sleep for 8 hours and staying awake for 16 hours. But what if we go to a planet that has a day that's only like 12 Earth hours long, and it's like 879 Earth days long, and everything's all thrown off? Are we still going to want to stay awake for 16 hours and sleep for 8 hours? Chances are our bodies will want that, but we're probably going to adjust in some sort of way. Like, the environment may have a harsher effect on our bodies, so we may need to sleep more or stay awake less, or gravity could be like a significant amount less, and we could stay awake for longer, and we won't be quite as tired by the end of the day. So we'll need something that will help us measure our days and not be specifically adapted to those planets. It'll be a necessity for those colonizing the planet to really take some time to decide what will be the right length of a day for the people on that planet, because the environment will have an effect on the amount of time that we want to sleep and the amount of time that we can stay awake, even if that day doesn't coincide with the day-night cycle of the planet that they're on. Because it's more important for a human's daily life to understand a specific amount of time that the daily routine can take. Beyond that, we can set up universal time measurement based on the speed of light. It's unlikely for our human bodies to be able to adapt completely to the day-night cycle of a planet. So if the planet has a 12-hour day, it's unlikely that we're going to stay awake for 10 hours and sleep for 2 hours. Our bodies just aren't going to do that. We may set up a calendar that's continuous, unlike the rotating one that we have here on Earth. I haven't figured out a measurement for time yet. I haven't put a whole lot of thought into that, and I'm running out of time on this video already. So if anybody has any ideas, just post them on the YouTube comments or in our Facebook wall. I'd love to hear what you guys think. DFTBA Brian, I'll see you on Thursday. Welcome to the end screen. Please subscribe to our channel and follow us on Facebook. We will love you forever. Also, check out these 2 randomly selected videos that we made among the other videos. Bye!